Good morning, everyone. Thank you so much for being here at the Casper Labs and Financial Times Lounge, the hub here in Davos, Switzerland. It's the annual meeting of the World Economic Forum 2024. I think for all of us who are here, we can all agree that the word we hear the most is artificial intelligence on the promenade in the Congress Center. And it is my pleasure today to bring to you two leading authorities in artificial intelligence and beyond. Professor Karl Friston, Chief Scientist at Verses and Professor at UCL in the UK. Karl, please. And Professor Yann LeCun, Vice President and Chief AI Scientist at Meta and Professor at New York University. Yann. Thank you very much to the two of you for taking the time to be with us today. You're very much in demand around the world, but especially this week in Davos. The reason we have put this panel together, this conversation between two rock stars when it comes to artificial intelligence, is to go beyond the buzz, to talk about the science behind it, to have an in-depth conversation about artificial intelligence. And as a warm-up, for starters, I'm going to ask you a question that took years for the European Commission and the people trying to regulate artificial intelligence at the European level to agree upon. What is your own personal definition of artificial intelligence, Karl?
So I've got the easy one. I should confess, I'm not an expert in artificial intelligence. He's the expert in artificial intelligence. I'm an expert in natural intelligence.
Boom. And so it starts.
So do you want me to define natural intelligence? Or
Please, well, here we go.
Natural intelligence for me is sentient behavior of the right kind. And I often think of that in terms of making sense of the world in order to make the right kinds of decisions. That usually boils down to some kind of inference, some kind of evidence accumulation, some kind of representing the causes of my interactions, my world, my niche, my eco-niche. Noting that, of course, my eco-niche is constituted by other things like me, in conversation, for example. So for me, intelligence is sense-making that can be characterized as gathering evidence for my world models and my generative models that make me fit for purpose in interacting with other agents.
Thank you. Yann.
So I think there's two types of definitions or views of it. The first one is very similar to what Karl just said, ability to perceive, remember, reason and plan. You said inference, but it's the same thing, a different word for the same thing, and then act. And there is this idea somehow that intelligence can be measured on a linear scale and that there are things that are more intelligent than others. This is completely false. Intelligence is a collection of skills and an ability to acquire new skills quickly, as fast as possible. The smarter you are, the faster you can learn. The more you know, the faster you can learn. But the collection of skills that you have or you can acquire may be different for one intelligent entity and another one. So humans, so this notion of artificial general intelligence is complete nonsense because human intelligence is very, very specialized. Like we're not general machines, we're extremely specialized. We're good at certain things. Animals are good at other things, not just because they have different perception, but also because their brain are built in a different way, and the motivations are different. Chimps are better than us at many things. So I don't think we can define a scale. And so for the EU to say, well, there's frontier models, right? How do we define this?
Yeah.
For the executive order of the White House, they say, well, if you use more than 10 to the 26 flops or something, you have to talk to us before because it might be dangerous. Now, notice that large language models that everybody is excited about do not do perception, do not have memory, do not do reasoning or inference, and do not generate actions. They don't do any of the things that intelligent systems do, or should do.
Which brings us back to psychology and ecological psychology, which is a theory that was born in the middle of the 20th century, studying not only what is happening inside the human, but the system, actor, environment, these perception, action cycles that, as you very accurately mentioned, are lacking today with artificial intelligence systems. We might have them in the future. Karl, you've been working your entire career on how the brain processes information, transforms information, makes inference. What do you think is the next step for artificial intelligence systems to add to what they're already doing in order to be able to do what Yann just mentioned, which is being able to process information, to reason, to sense?
Well, I think just to pick up on what Yann just said about planning, I think that's very, very important. And you could even frame this in terms of planning as inference, or inference in the service of planning. But just think about what that means to plan. It means that you're going to have the kind of world model or generative model in your head that entails or can predict the consequences of your action. And for me, that is definitive of an agent. So if I look at an artifact or another person or a particle or a virus, does it plan? Has it got the right kind of generative model or understanding of its own agency? So that, I think, is definitive of agents. And of course, now what we're talking about now is a move from artificial intelligence to intelligent agents. And your question, of course, is you're only an agent when you're interacting.
Exactly.
So we get to the distributed aspects, and that distribution is manifest wherever you look. I mean, from my point of view, how on earth do neural populations, as little agents, deciding who to listen to, who to attend to in terms of the presynaptic inputs and who to broadcast their messages to? It's all a game or a question of understanding how they coordinate, how they interact in the service of pursuing their own agency. And those principles, I think, will underwrite what you were talking about, sort of the, well, you can frame this in terms of evolutionary psychology, eco-niche construction, but also just federated inference, planning together, distributed cognition.
Yann?
Well, a lot of people, a long time ago thought about this idea that somehow intelligence emerges from interaction with the world. I mean, there was pioneering work by Andy Bartow and Rich Sutton about this, right? And that led to the entire branch of AI called reinforcement learning. So it's not just the idea that you learn from interaction with the world, but that's the only way you can learn. And there's even, position papers by people at DeepMind saying reward is all you need. Essentially, that's the main underlying principle to becoming intelligent. That turns out to be a complete failure. So DeepMind was founded around this idea that you're going to solve intelligence by using reinforcement learning. And yeah, you can train systems to play Go, to play chess, to play various games, to kind of adjust if you have lots of interactions. But that basically only works in virtual environments that you can simulate really quickly, because the time it takes to learn something through reinforcement learning is just insanely long. Even in very simple experiments to learn to play Atari games, it takes the best algorithms, tens of hours of equivalent real time to learn to get to the level
of a kid
that a kid can reach in 15 minutes. So, that tells you that we're missing something big in terms of how to learn. So one thing that Karl and I really agree on is this idea of mental world models, right?
Yeah.
The ability to learn how the world works, mostly by observation, a bit by interaction and experimentation. And the fact that we can, with this world model, predict in advance what the world is going to do, but also how the world is going to react to actions we might take. So we might imagine a sequence of actions, predict the outcome, and then if we have a goal to satisfy, that allows us to plan. So that's the inference process by which we optimize basically the sequence of actions that will satisfy the goal. And you can use Bayesian methods, which you are very fond of. Very a little less, but see this as an inference process, regardless of how the details of how you want to implement this. Now, in the context of things like LLM, there's none of this, right? There is no inference by optimization. There is no goal to direct the action the system might take. And so that's absent of any of those models. The only place in AI where those things appear is people working on robotics, and things that's called either optimal control or model-based reinforcement learning, where there is this idea of learning a role model by observing the world and then using it to learn tasks after the other. And that I wrote a position paper a little less than 2 years ago where I kind of explain how this could be done. I'm not giving a working system. We're still working on it, but it's where I think
a roadmap in that paper.
It's
for
a
whoever's
roadmap.
interested, this is the roadmap to read.
This is a roadmap for where I think AI research should go over the next 10 years to really make progress towards, animal-like intelligence.
I'm going to quote Karl, and we are all very familiar with René Descartes. I think, therefore I am. And one of the things that Karl has been an advocate of over the years is I am, therefore I think. Is it possible for you to explain briefly what lies behind this little twist, not only in history, but conceptually?
It's not possible for me. There are people who can do it briefly, but I'm not one of them. So I think what you're getting at is the physics of existence, just being, and what does it mean to be, and let's put it in the context of agents in a network, or people in a community, or nodes on a web. So to exist, to self-organize in a way that is sustainable and sustains the integrity of the way that you individuate yourself and everybody else, but you are also open to be synchronized and to be able to infer what other people mean and what other people's propositional stances and intentional stances are, then you can write down a physics of that. And I just want to mention the physics because there are two sort of themes that we could pursue here. There's going to be no debate here. We're on the same page, but there are two things I think we probably both want to foreground. Repeatedly, you've talked about the importance of doing things quickly, doing things efficiently. Your children learning within a few minutes at 20 watts. What you would take, what a large language model would take, a lot of electricity and a lot of resources. The other thing you've brought to the table is this sort of the fallacy of reward, the difficulty of casting the objective of the objective function of being as a reward function. So I think the physics really has something useful to say here. So the free energy principle is a principle of least action. It's a principle that allows you to write down, a principle or a method that just allows you to write down the right way of exchanging beliefs, acting upon the world and sensing that world that is as efficient as possible. It's the path of least effort, the path of least action, which is why Yann brings up the example of a child learning to play Atari games in a very different kind of way from you would find, say, in Deep RL.
What is your take on I am, therefore I think?
I mean, certainly if you are, you need some way of interpreting the world and acting in it for survival. And so yes, you need to think. Perhaps it's at a very simple level, but evolution seems to have figured out that the better you can interpret the world and figure out how it works, the better you can extract energy from it. Essentially, right? Because that's what survival is about.
Energy, absolutely.
Energy from it.
Both models.
So maybe there is another free energy principle there in our interaction with the world. I'm sure the psychophysicists have discussed this before. But I think there's an important point. So I don't know if it's formulated in terms of efficiency, but if you think about how much data are used today to train an LLM, okay, it's on the order of 10 trillion tokens. Token is like a word. And each token is about 2 bytes, so that's 10 to the 13 bytes to train a LLM. That seems like an unfathomable amount of information, right? It would actually take most of us here between 150,000 years and 200,000 years to read this, okay?
Take your time.
So you see LLMs, being trained on this. You say, oh my God, those things are incredibly smart. They can remember all that things. Like I can't even read it in multiple lifetimes. Okay, and then you talk to developmental psychologists like Linda Smith at University of Indiana, and she tells you, a 4-year-old has been awake a total of 16,000 hours. And you say, okay, 16,000 hours, multiply this by 3,600 seconds per hour, and then figure out what's the bandwidth of the optical nerve going to the cortex. It's about 20 megabytes, right? You have 1 million nerve fibers per eye, and it's about 10 bytes per second, right, give or take. So multiply, that's 10 to the 15 bytes by the time you're 4. 50 times more than whatever LLM, like the biggest LLM in the world, have been trained on, okay? So what that tells you is that in the space of a few months, the baby has seen more information than the biggest LLMs that we have. And
do the math.
And because this information is extremely redundant, there is a lot to learn from it, because you learn in self-supervised learning framework, you learn more if the data is more redundant. So the amount of information you learn about how the world works by just watching the world and then eventually interacting with it is just astonishing. And we don't do this. We don't know how to do this today with AI system. That's the problem we need to solve over the next few years. And I'll tell you a joke. It's not a joke. Those systems will not be generative. Because we try, it doesn't work. So what's the idea, right? Generative LLM, you take a piece of text, you remove some of the words. In autoregressive LLM, you only remove the last one. And then you train some gigantic neural net to predict the words that are missing. So, okay, let's apply this to video. Take a piece of video and train some gigantic neural net to predict what's going to happen next in the video. If the system can do this, then it has understood that there is, the world is three-dimensional, there are objects moving and others not, and they obey intuitive physics, blah, 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 right? So you should be able to do this. We started doing this, almost the first year that FAIR was created 10 years ago. We started imagining how we could do
AI research lab by Meta that you created and launched.
Which used to mean Facebook AI research. Now it means fundamental AI research because it's Meta. And so we started experimenting with systems that could do video prediction. We got nowhere. I mean, the system can sort of predict a little bit in the video, but the kind of representation of the world they learn from this is useless. And what I kind of completely changed my mind about 3-4 years ago by realizing that the systems that work best to learn image representations are not generative. They're not systems where you take an image and you corrupt it and you restore it, or video. They're systems that are called joint embedding. So you take an image and a corrupted version of it, and then you train encoders, neural nets, to encode the image so that you can recover the representation of the full from the representation of the corrupted. And that's not generative. You're not reconstructing pixels. It turns out you can't reconstruct pixels in images, just too complicated. So you have to use those non-generative architectures. So the future of AI is non-generative.
Well, you spoke about the future of AI. I would like to go a little bit in the past and talk about you two. We have leading authorities, which is very, very much an understatement in each of their respective fields. For people, they are royalty. I am French. I have, by history, a problem with the concept of royalty, so I will go with rock stars. But it's not been this way all the time. You both were very much ahead of your time. Karl in neuroscience, in how the brain functions, Yann with deep learning, and you had what we can call nowadays a winter in your career where you were promoting, you were working hard doing rigorous science. Meanwhile, your peers, the world, were not listening. Again, an understatement. I would love to know at a personal level how formative, how transformative those times in the dark, in the winter, how they determine what your careers are today, not only in academia, but in your transition to academia, from academia to the private sector. Oh, you should see Karl's look at the moment. This is the one thing you can emulate. He's like, seriously, Olivier?
I was just reflecting. No one ever listens to me apart from you, and now
I got a strong bias. I am a professor of neuroscience.
I know.
And an entrepreneur in AI. Come on.
Yes, we're designed to admire each other, and
Well, no. This way.
you should have asked him. I can't. He can answer that question. But I think there is a serious point here about pursuing the scientific process, and I mean that not as an ideology, but just as a reflection of something Yann was just talking about, which is an expression of curiosity, wanting to make sense of the world by exchanging and experimenting. So I'm just thinking about, while you were talking about the example of young children, how do they make sense of the world? Well, they do it by pinging and querying and moving. Can I move this? Can I move that? They learn about the move. They learn to perceive by acting. So this is active sensing, active inference, active vision. But so that agency, we come right back to the planning as inference and the agency that underwrites the sense making. That view inherits, or that view of curious children, curious creatures, I think it's just a description of all of us, but specifically scientists. That's what we do. We follow the scientific process. So you call them the winter years. I quite enjoyed them.
You didn't have to come to Davos back then, huh?
I see what you mean. Right, that kind of winter. Okay. Right. So for me, it's been a joyful, slow process of just pushing back, the frontiers of ignorance through being curious and doing experimentation. I would imagine very similar for
What about you, Yann?
Well, so I think when I go back to the early to mid 80s, when I started working on what was not yet called machine learning, neural nets, deep learning, or even AI, I thought the process was pretty much the kind of exponential growth that we see today, of course at a much lower level, but like the discovery and use of backpropagation back in the mid 80s. Before that there was some other work, Boston machines and stuff like that, and then the fact that we could actually build systems that could recognize real patterns with this, right, in the late 80s, which I contributed to with convolutional nets, and then what we call structure prediction now, which was like, how to have those systems kind of deal with more than just one object and do segmentation simultaneously with recognition. So that went until the mid 90s, and then so that's kind of an exponential curve, and that stops in the mid 90s because the entire community lost interest in neural nets. They thought it was too complicated to handle. There was no open source platforms that could be distributed, and so people had to re-implement their own neural net simulator, and it turns out to be really complicated, and there was no, kind of all the black art of how you make this work was not embedded in open source platforms. So a lot of people just gave up. And then, some new theory came in, Karl methods and stuff like that, which were much simpler to handle, and you can write beautiful math papers and books on this. So that captured the imagination of the academic world, not so much industry yet. So that was the mid 90s. And then for 6 years, I stopped working on machine learning altogether. This was the early days of the internet. I was working at AT&T, Bell Labs, that then became AT&T Labs. And I thought the internet could bring, knowledge to the world if we could scan documents and deliver them. And so I stopped working on machine learning. I worked on this project called DJVU, which is, a compression algorithm to distribute scanned documents. And then AT&T kind of disintegrated in the labs, at least in the early 2000s. So I left. That's when I became a professor and restarted that project of machine learning in the mid 2000s. In 2002, 2003. And then everybody was essentially mocking neural nets at the time in the machine learning community.
This is what I was alluding to.
That's right. And so Jeff Hinton, Yosha Benjo, and I got together and started a conspiracy funded by a Canadian foundation called CIFAR, Canadian Institute for Advanced Research. And we would organize, workshops, and you came to one of them. That's when I met you for the first time. A long time ago, and we started sort of bringing our students together, organizing summer schools, and sort of, inventing new methods and new algorithms to basically restart the interest of the community in neural nets, because we knew they worked. and writing open source platforms and stuff like that. And it started kind of progressing slowly around 2006 and 2007, where before that we couldn't publish a single paper in any machine learning conference, and after that we had a big enough community that the paper started getting accepted, and we organized a workshop at the NeurIPS conference at the time that had 600 people. I mean, it started to be very popular in 2007. And then around 2009-10, we started having results that really beat the state of the art in speech recognition. Working with people in industry doing this. And then 2012 was the ImageNet revolution when Jeff Hinton used convolutional net, my model, and got results that was so far ahead of everybody else that everybody said, okay, you win now,
Finally.
It's over. No, there was a big switch that went in the brain of everybody working on computer vision at the time. We have a person here who can confirm if I'm not describing this properly. He's from Zurich. He's not from Zurich, but he works in Zurich. And that's when the deep learning revolution started, and industry started getting interested in it. And then the revolution also happened 2 years later in natural language understanding and translation, and now it's everywhere, right? And so what happened was there was an exponential curve, and then in 1995 it went to 0. And then in 2003 it kind of restarted pretty much where we left off, and it kind of started growing slowly, and then boom.
A paradigm shift in Thomas Kuhn's words, huh?
You say it.
Yeah, I can say it. You're too humble to say it.
Too close to that.
Of course. Another thing you two have in common is the fact that you've transitioned to the private sector, but you still have more than a foot in academia. And I think this is crucial, not only to mentor and to grow the next generation of scientists that will benefit from your wealth of experience, but also to move beyond what we hear a lot today. I don't know about you two, but I'm starting to be fed up by hearing artificial intelligence everywhere. I'm more interested in objectives of AI systems and models and their outcomes, which is also how it should be regulated, in my opinion, based on outcomes. But I think you two have been way too civil to each other until now, so it's time to ask the question. We have here, he's too humble to say it, but the father of deep learning. And then we have there someone who now has a breakthrough claiming that they can go beyond deep learning. So how does that stand? How those two stances coexist to each other? Deep learning on one end and the breakthrough reverses that you might have that could be better than deep learning. And he gives me one of his looks once again.
Yes. Well, sorry, but there are questions under questions under questions. I actually see us as partners in crime here.
There we go. I hope so.
And we'll try and make it adversarial just for entertainment. Right. So I think deep learning is rubbish. Largely because it doesn't have the calculus or the machinery or the physics to have a calculus of beliefs, a calculus of inference, of planning, of situational awareness. And crucially, if you don't have a maths or an engineering toolkit that can quantify what you know and what you don't know, namely encode the uncertainty that underwrites your sense-making, you'll never know how to act in terms of getting the right kind of information. You were talking, Yann was talking before about sort of, the enormous amount of data and the way that it is smartly sampled by children, but not by large language models. They are very much dependent upon the data you give them. So one way of sort of drawing a bright line between the kind of linguistic capacity of large language models that inherit from, say, deep learning, and the way that we do it is that there is understanding there, and that understanding inherits from the fact that we use communication to query the world, to resolve our uncertainty. If you look at the imperatives for all of our action, they are certainly consistent with some constraints that some people might be, think of in terms of reward functions or cost functions, but 99% of it is this responding to epistemic affordances. What's going to resolve my uncertainty? What's going to increase my situational awareness so I can now make the right decisions through inference?
Point taken. Yann?
So I'm going to vehemently disagree with Karl by agreeing with him, okay?
Brilliant. En même temps.
En même temps. Okay, so first of all, I completely agree that to really have intelligent systems, we need systems that are capable of inference of the type that you talk about and I talk about by essentially marginalization, which is what free energy minimization does, or by just minimization, which is the zero temperature limit of free energy. But like, let's not go into the technical.
Oh, I want to do that. That's we're not allowed to do that here, are we?
Okay. So basically, you have an objective, you have a world model, you have an imagined sequence of actions or evidence about the world that you imagine is true, and you're trying to basically by inference figuring out what can I infer what I don't know from what I can observe, right? That's the principle of inference more generally. There's a whole bunch of people in the context of AI who have been working on this for many decades, working with Bayesian networks, graphical models, things, or even energy-based models, which is the type of things of this type that I've been advocating. So I completely agree with that. Okay, this is not at all incompatible with deep learning. In fact, it requires deep learning because the question is, how do you learn those systems? How do you train those systems? And to train those systems, you have to have some objective function you're going to minimize, and you're going to have some way of estimating what the gradient of that function is, so you can optimize it with respect to the parameters. And that's all deep learning really is. It's not incompatible with inference. What it is incompatible with, and where I would agree with you, is what is rubbish, you said, is feed-forward inference. Okay,
yeah.
So most of what deep learning systems are doing today is that you put an input, you run through a bunch of layers of a neural net, and out comes an output. And that process is very limiting in the sense that it's not, first of all, it's not Turing complete. You cannot compute every function with a reasonable amount of resources by just running through a finite number of layers. From the theoretical point of view, is not complete, right? Whereas a process by which you give an input and then you have an optimization process that figures out the output, that's Turing complete, okay? In the first case, any input, for any input, it takes a constant time to produce the output. In the second process, if the problem is harder, it's going to take longer for the system to figure out the answer. That's how we work, right? LLMs are of the first type. You give a prompt, it runs through a few layers, generates the next token, runs through a few layers, generate the next token, etc. So the amount of computation spent per token is fixed. It's not Turing complete. The only way you can change this is by basically coercing the system into generating more tokens, so it devotes more computation to the problem, but that's kind of a hack. It's a horrible hack. And so I agree with you, okay, that we need systems that can do inference of a more complex type by doing free energy minimization or energy minimization, whatever. Free energy minimization is energy minimization with a trade-off for entropy, okay? So that takes into account what you don't know.
So we are allowed to talk about it. Excellent.
Yes. So inference means, you're seeing a picture and instead of saying, this is a person, this is a glass, you're sort of inferring a distribution over possible categories, right? And that's a trade-off between sort of producing a definite answer and basically quantifying your uncertainty, right? So, and I agree, it's a good principle. I'm a big fan of it. I teach it. Okay. So that's the difference, but that's not incompatible with deep learning. In fact, I think deep learning is necessary. I have a bet, which is that 10 years, 20 years from now, AI systems will still be based on deep learning. This is the same with us because we don't know how to do learning other than any other way than by minimizing some objective. And we don't know how to efficiently minimize objectives other than by estimating the gradients. And the best way we have to estimate gradients in a complex system is through backpropagation. That's deep learning. Okay, did I convince you?
The last point I would love to discuss with you too is something that has not been discussed so far, as far as I know, this year in Davos, when it comes to artificial intelligence, is open source. Open source and open science, how important that is. Let me put a bit of context here. Recently, at the end of last year, I was in Paris, France, sitting front row, listening to three people, Xavier Niel, Rodolphe Saadé, and Eric Schmidt, launching a project called QTI, an open source independent lab, and Yann, you're an advisor to QTI.
It's non-profit too.
A non-profit, they all committed $100 million in order to support research and open source production of models in artificial intelligence. Today, people like me, AI entrepreneurs, would not be able to do R&D without open source tools. But here we're going beyond. We're going with open source foundation models. There is open science as well. I want to have your feel, with the wealth of experience that you two have, on the importance of open source and open science in the broader field of artificial intelligence, in business, in science, but also at the regulatory level. Everything needs to be considering embedding open source models, right? And especially, it's surprising for a lot of people who do not understand artificial intelligence that Yann and Meta have been such huge advocates and beyond of open source, but I think this is the benchmark.
Yeah, so I think you might ask yourself, why is it that progress is so fast in AI? And the answer is because there is a very fast way of exchanging scientific information, publications, open source code, and that's enabled the entire industry to progress, and the science to progress really fast. I've been a big advocate of open research, quick turnaround publication. So in the context of computer science, that means that publications are really mostly conference publications. They're not necessarily, like long papers and everything, but it's like stochastic gradient compared to full gradient. It's noisy, but it progresses faster. If you know what that means. If you don't know what that means, doesn't matter. So I've actually written pamphlets in the past on how we could reform the peer review system so that information exchange goes faster, that we don't keep good ideas under wrap for too long, things like that, which I tried to implement together with Yoshua Bengio by creating the ICLR conference. So ICLR, International Conference on Learning Representations, which is kind of the deep learning central, if you want, was created in 2013. In the 10 years, it's a very big conference now with thousands of participants. In the list from Google Scholar of the largest impact factor venues, it's number 10. It's above PNAS. It's above
legacy journals.
Yeah, I mean it's behind like Science, Nature, and a couple others. There's actually one other computer science conference there, CVPR, that's very high. But I mean that's astonishing, right? The impact that it's had, and it's because it has an open review process. It's very interesting.
It speaks volume about what the market and say the science market, but the business market need at the moment.
Right. So the modus operandi that has prevailed in AI machine learning particularly is you get an idea, you write a paper, you post it on archive.org immediately, then you submit it to a conference or a journal, then it gets officially presented or published. That usually is 6 months to a year later. Sometimes it gets rejected, so it might be a year and a half or 2 years. But at least it's out there, so people can see it. So let's take an example. The original paper on transformers, was it Transformer or BERT? I can't remember. One of the two. This paper had 700 citations before it was officially presented at the conference. And there's a lot of my papers that I never actually published. They're just on archive, and they have a few hundred citations. So what I want to say about open source, when I joined, before I joined Facebook, and I discussed with Mark Zuckerberg and Mark Schoffer, who was the CTO at the time, I told them, the only way to make a research lab work is for it to practice open research. If you have to incentivize people for publishing. You have to evaluate them in part on their publication and their impact on the external world, because otherwise you get fooled. The research you get is much higher quality if you ask people to publish it, because they have higher standards, right? And then you make the entire field progress, because the problem with AI is not whether we are ahead of Google or whatever. It's whether we have the technology we need for the future. And so the more people can contribute, the faster it goes.
Hence the alliance with IBM and other
hence,
companies.
10 years ago, working on open source platform, open sourcing all of our code, all of our platforms, building PyTorch, which now has become the universal standard in research for AI. You may not know this, but ChatGPT is built with PyTorch. That was built by Meta.
And Karl is the father of SPM. SPM is a toolbox that people like me, when we were students and academics, needed in order to process brain imaging data. And this is the same process. You contributed to the most used tool in brain imaging analysis.
Yeah, and it speaks to this, in fact, it comes back to one of your earlier questions about sort of, evolutionary psychology and cultural niche construction. The uptake is important, and if we build together, then we're going to get that right kind of emergentism from distributed cognition, but it does rest upon that open science ethos and ideology. So as academic, it can't be any other way, and indeed that's why I was attracted to Verses as a sort of taking that ideology, that notion of distributed cognition that could be facilitated by the right kind of message passing protocols and the right kind of standards that are just there to enable this kind of exchange and co-construction of some kind of universe, but a universe in which we're all resolving our uncertainty about each other.
Unfortunately, we need to wrap this session. My company, Inclusive Brains, makes brain-machine interfaces that are powered by AI and Gen AI. And in the name of my company, I want to thank Casper Labs NFT for having free consulting for our R&D in the coming months. I hosted a podcast in Davos called The Centaurs.ai. And the idea is the fact that the future is not about just human intelligence, not about artificial intelligence separately, but the combination of the two. I think you two embody what the centaurs are. And the last question I was asking my guests was about the thing that AI will never be able to replace. The very interesting answer I have amongst the very interesting answers was grit and determination, which I think speaks volume to and represents some of your careers, but also, I think, humbleness. And we have two leading lights in science and technology and business who are beyond humble. So thank you very much for everything you've done and the way you've shared it with the world. Thank you so much to the two of you.
Thank you.